Hi there, class. It's just me, Mr. Wee. I just wanted to go over some more things on 3.4. As review, in 3.4, we are talking about velocity and other rates of change. And I kind of talked about a rate of change of a shape in the last video. If you're going in order of the videos I have on my website currently in 2018, 2019. Go ahead and, well, basically, you're going to need to take notes from this entire page up and down. Um, and then I'm going to discuss what all this means. So basically, I'm going to have it in this position up here. Then I'm going to scroll up. I'm going to scroll up slowly. And I want you to do is I want you to just pause the video at various points to write all this stuff down. So go ahead if you need to pause this. And I'm going to slowly scroll up. So I want you to copy all of this down. The only things I don't want you to copy down are this: derivatives equals this, blah, blah, blah. And then there's a weird note to myself about some other stuff here that you don't need to know. Everything else, though, you need to write down. So go ahead and pause at various points. I'm going to scroll this slowly up. Okay, so let's go over this really quick. Position of an object. So when we're discussing derivatives, which we understand are slopes, and that's basically slopes at particularly one point or an instant in time. We also think of it as a change in y or a change in x, but just at one particular point. That's a derivative. Well, the theme of displacement, speed, velocity, acceleration, these are all interconnected. For any students that are in physics, you might have recognized these concepts as being interrelated to each other. This theme of velocity, acceleration, speed, and displacement are very good examples of derivatives to explain the concept of derivatives, or an example of what you could use derivatives in real life, or like an application of derivatives in real life, and trying to understand some concepts like speed, velocity, acceleration, etc. So the first thing you want to learn is, let's make like a function like y is equal to f of x for a position of an object. So that's where we start with before we start talking about the derivative and the changes of this position and so forth, okay? So it's really confusing because we use S, and so does the book, and a lot of other sources use S as position of an object. A lot of people misconstrue that as speed, so please don't do that. S is purely a position, and it is a function of your input value of t, which stands for time, okay? S, again, is a value that will give you a position of an object if you put in time. So, again, write that down. S is equal to position, which is a function with respect to time, f of t, or like the function of time would be right here, f of t, and the time itself would be like a variable, an independent variable. So what does that look like? Well, if I had to draw a stick figure person, right? If I had to draw a stick figure person, right? Okay. At t of 0, at 0 seconds, this person is in a position, right? We can arbitrarily say that this position is, I don't know, or remember, S denotes position. So his or her position, this person's position would be like at position 1, let's say, the initial start, okay? And then after t of 2 seconds, this person kind of moved in this direction, is now at a position of 3. We can arbitrarily put that at any point. We could say it's like at 1 meter. Let's say we can give it a unit, and then after 2 seconds, this person is at 3 meters, okay? Right? So basically, there's some kind of formula. That if you put in at 0, we don't know what it looks like, but it's like some kind of equation, right? Like t plus t squared. We don't know what it is, but I just know that when you plug in 0 time, This person's position is at 1 meter. Does that make sense? Okay, not too hard of a concept to understand, huh? And then let's say that this person again, right? Same person, unbelievable or not, after 5 seconds is now at 5 meters. Okay, let's say that. So what that would look like is S, which is a position, which is a function of position. If you put in 5 seconds, right? This is, you have to put in a time in this equation. Again, we don't know what the equation looks like. It could be t plus t squared for all we know. We get out 5 meters. Okay, so hopefully I drilled that enough into you to understand what this is. Okay. And then we have the next thing, which is a change, okay? A displacement of object over time, okay? So this is, if you look at this, this is delta S. That means there's a change of position. So some other things is like a change of position could be denoted as delta S, which stands for position, which is f of t plus delta t minus f of t. So what is that going to look like? And you don't divide by t, okay? So just keep that in mind because this can get kind of confusing with the next thing I'm going to talk about. So displacement simply the change in S, okay? So let's say I want to take the difference between here to where this person was here. I mean, from this person to this person here, okay? So again, I know this is confusing, or this can get a little confusing, so bear with me here. The change in the S, okay, as you can see, is simply you just subtract the position that this person is at now, right? The second position, 5 meters, minus 1 meter. And then you see how much this person moved. This person was displaced. This person is now 4 meters, positively 4 meters ahead. Okay, not too bad. Not too bad to understand, right? So what is the whole f of t plus like delta t minus f of t going to look like? Well, that's pretty simple. What is the change in the time? Well, 0 to 5 seconds, you just subtract 5 minus 0, and then that would just be like, so it would be t plus the change. So that t would be f of 0, right? And then you add that difference in the time. So we know that this lurching forward is 5 seconds. So you just add that 5 seconds. I'm just going over concept here. This isn't like going to solve any problems really in your homework, but you need to understand what all this is. In f of t, the original start was at 0 seconds, right? That's it. But remember, I'm not talking about I'm not talking about like 4 meters over any time. I'm just looking at the change in the displacement. But how you'd write the notation would be like the function of t plus the delta t. So it'd be the function of 5 seconds minus the function of 0 seconds. But again, we don't actually do anything with the time. We don't like divide meters by time. We don't do anything. So this is purely just a change in your position, okay, by 4 meters, right? That brings me to this next point, average velocity. So when you hear average, that's a key word, you have to think of a secant slope, which means of 2 positions. So that's 2 coordinates, okay? So now we look at what we did. We take the displacement and we put it over to the travel time to find out how fast did this person go, the average time, the average velocity, okay? So you would take the delta S and now you would divide it by the delta T. So it would look like this. The f of t plus delta t minus f of t, now actually divided by the actual difference in time. T plus delta t minus t. And then you'd get this nice equation because t plus, I mean, if you think about the math here, t plus delta t minus t, these t's will cancel out. You're just looking at the delta t. And I'm going to show you what that looks like in just a second in my example, okay? And then this is, and I wrote in red that this is no different from just doing a change in y over a change in x, y2 minus y1 or x2 minus x1. So again, let's take a look at my example here. This person here, let's see. So displacement, or now we're looking at the average velocity. The average velocity of this person, right? You would do the delta S over delta T. We already have delta S. I've shown you how to do that. It was just like 5 meters minus 1 meter is equal to 4 meters, right? And technically what that looks like is F of 5 seconds, or 0 seconds plus 5 seconds, right? Minus F of 0 over delta T. So it looks like T plus delta T. So T was at 0 seconds, right? And then the change, so T was at 0 seconds. And then you have to add the delta T, the change, the difference between 0 seconds and 5 seconds. Well, you subtract 5 minus 0, and that's still 5. And you subtract the original time. So let's take a look at what that looks like. Everything on the bottom is in seconds. So 0 minus 0 is just 0. And then you have 5 seconds now. Okay. And then up here, if you remember the function, the f of 0 plus 5, the f of 5 seconds, the function of 5 seconds, which is equal to s, the s would be, the s would be 5 meters. We're looking at 5 meters minus 1 meter. 1 meter because the s, which is equal to f of t, or f of 0, right? F of 0 would be 1 meter. Okay, now let's calculate this person's average velocity. That's 4 meters for every 5 seconds. And I think if you do the math, it should be 0.8 meters per second. That's how fast this person is going. Why is it that we call it average? Well, for one, we know it's between 2 points. It's not at an instant, right? But think about it this way. I say that it's average because the person, right? Let's look at a visual of this person, right? Let's say that at t equals 0 seconds, and at the s, or the position this person's at, is 1 meter, right? Now, I know I had this example, but let's cross this out and pretend that never happened. All we have, the information, is where this person was at 0 seconds and where this person was at 5 seconds. Let's pretend that we didn't have this value in the middle, okay? So I do apologize. And then let's have the endpoint over here of this person being here. Like he was in the middle of running, right? Whoops. That's his shoe, okay? Okay, I'm sorry, I'm getting a little bit too detail oriented. Okay, so he's in the middle of running. And at t is equal to 0 seconds, or 5 seconds, right? S would be 5 meters. Okay, so theoretically, what we're thinking is average velocity. The average change in this is, we would think this person consistently runs at 0.8 meters per second. That means on average, between here to here in the interval that this person ran, you would think this person ran at 0.8 meters per second, okay, the whole way. So that means after 1 second, we should expect the person to be at, well, if it's 0.8 meters per second, after 1 second, this person goes up by 0.8 meters. We should expect him to be at 1.8 meters, right? So we would expect the same running, right? But is that always true? Like, it's like in a car. If you're in a car, right? If you're in a car, and you drive at an average, like after 1 hour, you're on the freeway and you drive 60 miles, right? But did you go 60 miles per hour the whole time in that hour? Well, no, because you don't know how traffic was. You might have ran 80 miles an hour for 5 minutes, and then there's a traffic jam somewhere in LA, and then you had to slow down to 20 miles per hour. And then so I'm just saying the average after 1 hour is you traveled 60 miles per hour. So you traveled 60 miles, so your average velocity is 60 miles per hour. But does that mean you rode 60 miles per hour all the way? Well, not always. So let's just say that at this instant, what if this person traveled 4 meters? Like he ran super fast. Hair's flying back. Okay. This person ran super fast after 1 second, right? But then let's draw an in between guy. Let's draw him in red. I know it's kind of hard to see, but let's say this person. No, let's because red doesn't work. Blue. There we are. Faithful. This person now at t is equal to 2 seconds only travels. He's only at a position of 4.2 meters. So do you see that in a span of 5 seconds, we would think the average velocity as 0.8 meters per second, right? But you can clearly see the velocity between here to here is much faster. You would take like 4 minus 1, that's 3 divided by 1. He's going 3 meters per second from here to here, right? But then from here to here, if you took the difference, right, it would be like 4.2 minus 4, that's 0.2 divided by a difference of 1 second, that's 0.2 meters a second, right? But then if you do the whole thing from here to here, the average would be 0.8 meters per second. So this only gives us an average, but it doesn't give us the whole picture, okay? So that's kind of why I wanted to talk about all this stuff that averages, because it explains how a slope between two coordinates is completely different from finding a slope or derivative, which is a slope at one point in instant. Yeah. Okay. So let's look at not the average velocity, but the instantaneous or the instantaneous velocity. It's the derivative. So that's why we don't call it a slope. It's like a special slope, a slope at one point, the derivative of your position function. It's not a secant, but a tangent. Sorry if you can't read that. It's a tangent. Okay. Tangent. So we don't do delta s over delta t because that's a change over a change. That gives us an average. What we're going to look at is ds over dt, which you can look at as the derivative of s over derivative t, or more appropriately, that's the derivative of your s function, which is position, with respect to the independent variable time, t. We would normally take that with the limit of, you would take it as the limit of a delta t approaches 0, and you would pick a point. You've seen this already, but I guess for our example here, let's say we wanted to find the instant this person right here. Let's focus on this guy right here. Let's focus on him. Let me try to redraw him really quick. Let's focus on that weird instant. Remember that in 5 seconds, the average, you don't have to write this, okay? The average velocity of this person. In fact, all of this drawing, I don't know if you really want to write any of this, if it helps, okay? So I do apologize. I'm just trying to show you so you can understand. And average velocity was 0.8 meters per second. That's how this person traveled in, in 5 seconds, right? But let's focus on that one example that I had. So I'm not going to draw it perfectly. Here's flying back. Okay. And we knew that at t is equal to 1 second, that person's position was at 4 meters, right? But I'm not asking for the average velocity, which is this. I'm not asking for this. I'm asking what is this person's instantaneous velocity at t is equal to 1 second. At 1 second. So I don't ask for this, but I am now asking for this right here. So what that would look like from the traditional way is the limit as h approaches 0 if we're looking at f of what is it, 1 second, 1 second plus this imaginary difference, right? Like just like maybe like g, where is he at t is equal to 1 second plus h, right? Where is this, I don't even know what this person's, like position would be, right? If you add h seconds, right? We're talking a difference of h, right? H seconds, right? That from this person to this person or wherever this person is. But we're saying is if that h, that gap between these two positions goes down to 0, we approach a slope or a derivative, an instantaneous slope. So it'd be here minus f of 1 second over, it'd be 1 second plus h minus 1 second, which would basically give me the limit as h approaches 0. We can clean this up. That'd be f of 1 plus h minus f of 1, right? All over 1 second minus 1 second, you'd have h. Does that make sense? So that's nothing different from what we've been learning. I'm just asking what the heck is that person's instantaneous velocity at that instantaneous speed, okay? All right, and again, I can't solve this yet because I have no idea what the heck the equation is. If I did know, if it was like t plus t squared, remember I said that earlier, right? Then I could solve for it and I can plug it in this guy, but I don't know. I just gave you a function of t, and all you know is that the function of t is equal to another letter like s, just like f of x. Sorry, this is t, just like f of x is equal to y, right? It's the same thing, okay? It's the same idea, right? Okie dokie. So I hope you're still coming along with me here. Speed and instantaneous velocity are almost directly the same, okay? Why is it, though, that they're differentiated? Well, look at the difference. This is ds of dt. This is ds of dt of... in brackets, what the heck does that mean? Okay, so another way of denoting velocity that I didn't talk about is you could look at it as v of t. So the v of t is equal to the first, you do want to write this, derivative of position to the position function. So this is the first derivative. So when you take the derivative one time of s, of the equation s, you will then get the instantaneous velocity. So another way of saying it is the velocity of time is equal to the derivative of s, the first derivative of function, the position function. Speed is almost the exact same thing, only you have absolute value. You're looking at the absolute value. And why is that particularly important? Well, look at this. Every time we talk about this person's velocity, we're always going forward. I want to do another color. Okay, so blue. We're always going forward, right? Velocity. Velocity, what if this person traveled the same speed going backwards? Whoosh, like this. So let's just say at this person, I said, like, let's say roughly his derivative would be like 3 meters per second or something. It's like 3.8, 3.9 meters per second. If the person went backwards, it's now negative 3 point blah, 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 blah meters per second, right? This person going backwards. Or what if this person went backwards this way or this way? I don't know. Well, it would change the sign. Well, speed, however, does not matter. Speed, I do not care if this person goes backwards or forwards. I just want to know the magnitude at which how fast that person was going. So velocity does take into account the direction you're going to. Speed does not. I just want to see purely how fast that person was going forward or backwards. Okay? All right. And acceleration. Okay, so I know this one's going to be a little bit harder to show, but simply put, it's the derivative of velocity, how the velocity changes in itself. Okay, so I know it's weird. Another way of saying this is it's the second derivative. Oh, sorry, the second derivative. If you take the derivative one more time, the second derivative of your position function. Hopefully this will make sense in my example, okay? The second derivative of your position function. So that's why I have d2s, d. So if you had like, let's say, okay, you know what? I didn't want to do this, but let's go ahead and do it. S, again, is f of t. And let's say he is t squared or t cubed minus 3, right? If we wanted to find ds dt, the velocity, a equation for velocity, we would have to take the derivative of this guy here, which would be df of dt, if you want to write that. So remember, s is synonymous with f of t, so saying the derivative of s with respect to t is saying the same thing as the derivative of f of t with respect to t. This, you do the power rule, you take the 3 in the front, and then subtract 1 from the exponent, and then the derivative of a constant would be 0. So if you want to find the equation for acceleration, that would be dv over dt. I think the way I wrote it, though, you don't have to write the t in there. You just write dv over dt. It really doesn't matter if you put the parentheses t in there. You can just put dv over dt or dv of t over t. I know it's really confusing. Which is the second derivative of position. Remember, s is for position, not speed. I know it's weird. I just chose s to be position. Inconveniently, I'm very sorry. Okay, over dt. I think, dt, or it looks like dt squared, but you don't do anything to the value or anything on the bottom. Okay, it's just notation, purely notation stuff, which is the second derivative. Of f of t over dt2. You take the derivative of this. The 2 goes on the front, so it's 2 times 3 times t. You take 1 away from 2, and that's just 1, and then the derivative of 0 would just be not there. So it'd be 6t. So these are, you just solve for this, okay? Basically, if I was given an actual equation for position, t3 minus t cubed minus 3, its velocity, you can plug in time at any time. You can find out the velocity by just having this guy here, this equation, because I took the derivative of him, okay, which is 3t squared, right? I just plug in any time I want to put in there, and I'll figure out what its velocity is there. And then not even more important, but equally as important or equally as cool, is if I take the derivative of this guy, I will find the change in the acceleration. Okay, so conceptually speaking, what is acceleration? Okay, all I can say is, look, here, no velocity. Here, a very fast instant velocity. Here, the instant velocity is a lot slower. Here, the instant velocity is in between these guys, right? How did the velocity change, though? It's like your car accelerating. When you press on the pedal, you see it accelerating up. It goes up in speed super fast. And then maybe for the next few miles, you just ease your foot in just a little bit more. You see that? You're just adding a little bit more velocity. How does that velocity change? How that velocity changes is your acceleration. So again, instantaneous velocity, not fast, super fast, very slow, and then somewhere in the middle. But how that change of how did it change from not or to super slow to super fast? That change in how that velocity is. I know you don't have to get this 100%, but you just have to say this to yourself, okay, at least. The change in how this person went from super slow to super fast, okay, how the velocity changes is acceleration. So again, you have position. He's there. He's now at 4 meters at 1 second. At 2 seconds, he's at 4.2 meters. And at 0 seconds, he's at 5 meters, right? Okay, good. We got that. The average change from here to here, right? That's average velocity. And it's about 0.8 meters per second if I had taken average. But if you look at the instant, at this instant, he's running super fast. At this instant, he's super slow. At this instant, he's kind of fast. This instant, he's not moving at all. But if you look at how it changed, how did those instances change? How did the instance from here to here change? Like this, that velocity at this instant, how did it change? That's where we talk about acceleration. Okay. All right, guys. I think I talked enough. That's all concept. The next video will be the last video, and it will be through an actual. Oh, let's see. Let me see if it is that. I think I have 2 more videos worth of stuff for you guys. Okay. So next video, we're going to talk about an example. It's going to be number 13, page 138. We're going to go through that. And then my last video will be on example number 9, page 138. Okay, guys, you guys have a grand day. Okay, so tune in for the next video. Goodbye.